So next up we have Harry Van Haren, and he's going to talk about service cores.
Phone. Can you hear me okay? Yes. Fantastic. Hey everyone, Harry Van Haren is my name. For those of you who don't know me, I'm working for Intel. I'm working on DPDK down in Shannon, so with a bunch of the folks here from the team. Today I'd like to talk a little bit about service cores. So you might not be familiar with service cores yet. It's pretty new. It got merged in August at the start. The patches have been floating around on Patchwork for a while. But yeah, I'll let you know what service cores is about and kind of take you through it. So, excuse me. Quick overview of what we'll have a talk about. First of all, I'll try and describe what problem service cores addresses. So some people in the audience might not be familiar with exactly what service cores tries to achieve. So first of all, a problem statement. What's currently an issue in DPDK that service cores is going to try and solve. So the next slide then is kind of a goal. How or what are we trying to solve? Then we're going to talk through a couple of the details of what code is currently in place in DPDK EAL in order to solve that problem, so the solution. I'll talk through an example of the event dev and using the software poll mode driver with event dev to showcase where this service cores actually can be used in and yeah, how it solves the problem there. And then I'm going to open it up to a lot of discussion. So I only have a few slides and I'd really like to get your input on how service cores could benefit either your application or somehow how it can interact with what you're trying to achieve with DPDK. So from that, let's have a look at the problem statement. Most people in the audience are probably familiar either with ethdev, cryptodev, event dev, or one of the other device subtrees. Ultimately, all of these device subsystems have either some kind of hardware available to perform a task, whether that's either for event dev scheduling, or ethdev transmitting or receiving packets, or cryptodev performing some kind of checksums or calculations. There's going to be hardware available to that, or it's going to be implemented as a software fallback. The whole point here being that if your specific platform doesn't support hardware or doesn't have hardware available to perform a task, that there's a software fallback available for that, and due to that, your application can continue to function correctly because the functionality is going to be taking place. It might take place on a CPU core, perhaps it's slower, but ultimately your application will function. So that's kind of the tagline, that when we have this abstraction of ethDevs or event devs, if we have hardware, we can perform hardware-accelerated functionality. If we don't have hardware, then there's a software functionality or software PMD providing that functionality. And the difference between those two is what service cores actually solves. So if we have hardware available, then there is no L core or no DPDK CPU core required in order to actually perform that function. If, on the other hand, we're using a software poll mode driver as a fallback for that functionality, it's obviously going to need some CPU cycles to actually perform that task. So what I'm trying to say here is that the difference between running something on hardware and running it in software, using a software PMD, is an L core. So what we're ultimately struggling with here is that the application needs to be aware of, are we running on a hardware PMD or are we running on a software PMD? Because either the application logic has to call a particular function, aka run the software PMD, or not. Perfect segue from Christian and Jasvinder's talk previously, SoftNIC requires CPU in order to perform its SoftNIC capabilities. Where does that CPU L core come from? Does the application, every application in this case, need to actually include that threading logic of should I call RT L core remote launch into this SoftNIC function, or does that core appear out of nowhere? You know, what happens here? So the punchline of this slide and of the problem statement that service cores wants to solve is that the environment you run in has different L core requirements. And what I mean by that is, do you have hardware capability for the function, or are you running a software PMD? That's the summary. So let's look. What does service cores try to do? Well, because there is a difference, the DPDK EAL, the environment abstraction layer, should abstract that L core difference of your platform. So if your platform has hardware capabilities, you don't need a core, otherwise you do. There's a difference there. That difference is what should be abstracted by service cores. And ultimately, or ideally rather, doing that or abstracting that out will not have any application code changes. So what we're trying to do is not have every application be impacted or somehow have to call specific functions to set up this service core stuff. It should just be inside the DPDK EAL itself. and it should be self-contained, and it should just handle the difference in your platform. So the EAL, the environment abstraction layer, should also abstract any L-core differences based on if you're using hardware Poll Mode driver or a software Poll Mode driver. So that's the goal of Service Cores Library. When I start talking about the solution, we have two core components or core concepts in the Service Cores Library. Ultimately, there's the service itself. A service is a runnable work item. We can think of it as just basically a callback function. It runs an iteration of work. An iteration can pretty much be defined by the particular function being performed. In case of an Ethernet device, perhaps receive or transmit a burst of packets. In the case of an event dev, perhaps schedule any available packets and then return, or schedule 512 events and then return. So the important thing there is basically it's just a callback function. I think most people here in the room are developers, so you probably prefer the graffiti function type thing. Then we'll talk about a service core. So the service itself is a callback function that needs to be called periodically in order to have our DPDK application perform its function, whereas the service core is an L core, typically just an ordinary DPDK EAL L core, that's dedicated to running services. So there's an important distinction here that this L core is dedicated to running services. It's not available to the application. In bold here, it's removed from the application core mask. And this is one of the points where ideally we wouldn't have to do this, but I don't see a different technical solution possible. The reason that we remove it from the application core mask is because we need to run a function on this that will basically iterate through the services. So we could have, let's say, two services, one to run our softNIC and one to run the event dev software Poll Mode driver. And those two functions should be called one after the other continuously in order to keep packets flowing through the system. So what happens when we call remote launch from a DPDK application is that thread calls into an application function which could have a while one statement in it. We're never getting that thread back. So there's no way we can know if the other services are going to be run. The only way we can keep control of this thread is literally by removing it from the application core mask, keeping it to ourselves, that's being EAL really, and adding a main loop in the service library itself. So the main loop in this service library is just going to loop over the services. That's the core concept behind service cores. So we're stealing one L core from EAL, or rather, from the application. So at EAL initialization time, if we require service cores to be enabled, we take an L core or multiple L cores depending on the EAL arguments passed, and there's APIs for all of this stuff. I'll talk more about that in a second. And we make that L core available to run functions. In this case, functions are services in the library. So while one for each service, just call the service function pointer. An interesting thing to note here is that a service shouldn't be aware of which L core is calling it. So it should be agnostic to if it's called on L core 1, 2, 3, or 4. It shouldn't matter to the behavior of the function itself, because the idea is that we can actually migrate these services between cores. More on that later too. Just before we get to the really fun stuff, which is the Q&A, by the way, we're going to talk a little bit about mapping. So if we have one service core and we have multiple services, then we need to enable these services on the core. That basically means the core itself is going to call into this service and run it. If we have multiple service cores, so for instance we have 3, but say we have 6 services, there's a variety of ways that we can orchestrate those services onto those service cores. So it's like a many-to-many type mapping. If you have a bit of a graphical mind, then perhaps like seeing 4 services across and 2 down in terms of cores that can run them, you have a 4x2 matrix of options that you can checkbox if you want a core to run a service or not. Something like this is perhaps a simpler graphical depiction. We have 2 service cores, we have 2 services. We could either run them one service on one core, or we could, for example, turn this off and move that monitoring stat service to core 1 as well. So there's options here in terms of how we map or orchestrate or have services run on a service core. So that provides a lot of flexibility. That's ultimately what I'm trying to get to here, that with the service cores library, we're not just getting a core to run a function. There's actually a lot more to the service cores library in that we can schedule different functions on different cores. Multiple services on one core being kind of a simple enough option. Multiple cores all running one service is also an option. There is a multi-thread safe flag for the service itself. So if you have, for example, an ETHDEV that's capable of transmitting on multiple queues at once, for example, you could have multiple CPUs actually call the same service. So lots of options. Exactly how that fits your use case and things like that is something that we can get onto. So at this point, I do encourage you guys in the audience, have a think about your questions and answers. Where does this service core stuff fit into your DPDK use case? Do you have a service that you'd like to have run by DPDK or from an application? And what I'll do first is talk through the event-dev software Pulmo driver example. Hopefully that will give you a bit of a real-world use case as to where this service core is, how it can be used in a production environment. And then afterwards, I'm going to open it up for discussion. So hopefully in a minute or two, I'll be done with this, and then we'll have 15 minutes-ish for questions, answers. So talking about the event-dev example, we have an application that is using the event-dev software Pulmo driver. For those not familiar with event-dev, it's doing scheduling of events across cores. The software Pulmo driver is a software implementation to perform the scheduling for you. It is usually, or let's say always, an essential part of your application pipeline. So if you have multiple cores performing stages of work, this event-dev API and the software Pulmo driver will perform the scheduling to progress these events from one stage to the next stage, ultimately causing your traffic to flow the whole pipeline and then get TX'd on the other side. So that event-dev software Pulmo driver is, in this case, an essential part of your pipeline. If we don't run it, if we don't call schedule on that Pulmo driver, it's not going to function. Your application will stall. That's going to be different if you did have a hardware block for the event-dev, then the hardware will perform the scheduling. No CPU L-core will be required. So this is where that difference comes in between having hardware available or not. So in the software Pulmo case, again, let's say we pass these EAL arguments. We run our application called app. We pass in the --vdev parameter to create a virtual device. It creates the event underscore SW0. That's the name given to the software event-dev PMD. And what that will actually do is the next bullet point. It registers a service. So at creation time, when we create this event-dev Pulmo driver, it registers a service. What that means is the DPDK EAL becomes aware that a service has been registered, and that probably is going to require CPU cycles in order to run. What the user also does in this case is passes a service core mask. So in this case, the fifth L core is going to be passed to run a service for DPDK. So at EAL init time, it's actually going to initialize the service core's library because it realizes it's been passed this flag, so the user wants to enable that functionality. And it's going to create the mappings from the cores that have been enabled to the services that have been registered already. In this case, the VDEV software event-dev Pulmo driver service is going to be mapped to L-core 5. So EAL will do a basic round-robin distribution of the services to the L-cores. And in doing so, what we've actually achieved is that the application doesn't need to care if it's running on hardware or software. Because if the software is requiring an L-core to actually run, the user can pass it in. I'll just skip back here to the core mask. The user can specify the L-core mask to use to run those services without affecting application code. So the same application will actually run on a platform capable with hardware scheduling or a platform with the software fallback using the exact same code path. There's no code path at the application level differences. So the one difference that there is from the application's point of view in this case is that there is one less L-core available in the core mask because the EAL will take this particular service core out of the mask that's later passed to the application. So the application sees one less core, but the software Pulmo driver runs transparently to the application. So that's the trade-off there. The really nice thing is that the application isn't concerned with what I'm calling possibly required in the sense of does your hardware platform or does your platform support hardware scheduling or not? And does the application need to be aware of that logic? Should it spawn a thread into this or not? That's all abstracted from the application level. So the application can get on with providing functionality like useful work, whereas the DPDK service cores library now abstracts that difference like the environment abstraction layer should. So end result is that this RT event schedule function, which is currently being called, doesn't need to be called anymore by the application, like manually, shall we say, because the DPDK service is actually, or the software event of pull mode driver service is going to handle that. I mentioned earlier that it initially was merged in 1708. The APIs have been updated to 1711. After the initial design, there was a lot of usability improvements that became apparent from having designed the API that went into 1708. So rather than try and keep it backwards compatible, it's merged with the experimental tag. So ABI compatibility currently isn't an issue with this library. We made a decision basically to move the API up to a much more usable and user-friendly API. So it is currently merged in the head of Git. So I do recommend grab DPDK from Git. I sent a patch yesterday, that's the patchwork ID, for a sample application. It's a really simple application that registers 5 services and iterates through profiles of running different cores to those services. Difficult to describe, just download it and run it. It becomes really apparent. Keep an eye on HTOP or your favorite CPU monitoring tool and you'll get what's going on. With that, I'd like to open the floor to discussions, questions, if there's anything. I see there's some hands gone up, so could the folks with the microphones please have a look. So yeah, I'm open to any questions, both implementation details of the service core library or use cases or things like this. I have a couple of pet projects that I'd like to kind of enable with service cores, but I'm very interested to hear your opinions first. So with that, Martin.
So I've been asking a lot of questions. I better introduce myself. My name is Morten. I'm from SmartShare Systems. We do bandwidth management appliances. So I have a bit of critique on this and the softnik. So I think the softnik is just a special case of a pipeline stage. And I think the service core framework is just a special case of a scheduler. I don't understand why we need to implement special APIs for something that are just special cases of a generic scenario.
I'll try and answer the service cores part because that's more my domain. But ultimately, I understand the question is that you see service cores as kind of a scheduler for different functionalities across the CPU core, correct? And you're curious why we need that in DPDK as opposed to?
As opposed to a generic scheduler. This is scheduling specific pipeline stages with a special scheduler in just generic scheduler with generic pipeline stages?
So the way I see it is what service core is enabled. I don't think I'm going to directly answer your question, but I'll try and show what I see the value in service cores as, is that it allows us to add functionality to DPDK in a transparent way that the application doesn't realize. So I'm not particularly trying to become a scheduler in DPDK. I'd agree with you, there's probably little value in that. Where I see the value is that we can add these services without the application being aware of it, so it provides a level of abstraction.
Yes, and that leads me back to one of my questions previously today. Why do I need to do this at configuration time and not at runtime?
Right.
And so, for example, let's say I have a NIC that has hardware features, so it doesn't need the service core for the traffic management or whatever.
Yep.
And then I hot plug another NIC that requires a service core, and then I can't do it because I didn't allocate one at configuration time.
There are APIs for everything in the service cores library. You can dynamically add, remove, start, stop, everything, service cores and services themselves. So the sample application that I linked actually does this. It turns on and off service cores at runtime and showcases the dynamicity, how dynamic the service cores library actually is. So there has been thought for that use case in order to enable like more dynamic runtime usage of service cores. And ultimately, I'll go to my little cheat slide at the end. This is two like performance scale down type scenarios that I could imagine where we can add more cores in order to scale up, because here we have 2 cores running and the services map to each core uniquely, the performance setting. And on the other side, we have one core asleep because there's not much traffic coming in and both services being mapped to the same L core. So that's very, very easy to do in the service cores library with services. Again, I do encourage you to have a look at the sample app. It showcases pretty much this scenario with a slightly more worked out code base. So, yep, sure.
So I'll just jump in there as well. I was involved in a discussion with Harry. We sit in cubes next to each other in Intel, so in the design of some of this. So for me, one of the key points of this is that it provides a way for other components in DPDK, particularly things like drivers, to indicate that they need core resources for processing. So especially in the case of things like software fallbacks. Without that, it's very awkward to, the application basically has to start going and asking each one of its drivers, do you need a CPU to do your, your SmartNIC offloads or your event dev offloads? Whereas in this way, as part of the driver init calls the service core API just saying register a service. And with that, then the application or the EAL and then can then be queried by the application knows this particular component is not doing everything in hardware. It needs some core time to actually do its work. And thereafter, the application itself or the user via the command line can say, okay, I have 4 components that need core time. I will dedicate 2 cores to those 4 components, or I'll dedicate a core each, something like that. So that's not so much the scheduler. I see a lot of the value in just being able to say, I need core time. I'm pretending to do a hardware function, but I really need a CPU to do the work. So that's where it really came out of. If I have clarified things a bit more, I hope.
There's a couple.
Hey, back here. Can you hear me?
Yeah, sure. Go ahead, Roger.
So the service core mask, is that a subset of the L core mask?
Yes, very good question. I considered implementing this in various ways. It is a subset of the core mask. The reason for this is because if you don't need the service cores, you don't probably want to have your orchestration or your whole EAL command line become dependent on each other. So by actually stealing a core from the existing core mask that DPDK already takes, we, or at least I hope and think, that this will make it easier in order to deploy on platforms regardless of their hardware and software capabilities.
So if I assign 1 or more cores in that service core mask, are those core, they've now been carved away from my core mask. And I start up, so the service core infrastructure or whatever is started up on those cores. Those cores are sitting there burning at 100%, doing whatever services get assigned to them. And one of the issues we had early on with DPDK was you could run one thing on an L core and it ran all the time. And so we're running in a virtual environment where people are paying for CPU cycles, right? So if I have service cores that I don't have a way to prevent them from throttling themselves, shutting down and taking a break if they're actually just calling something that does nothing, because there's no work to do, I'm just polling whatever this thing is, right? So do you have anything built in to be able to, take a break? Some hysteresis or something? Very
good question. I don't see that as part of the service library itself. I'd see that more as a service itself. So if you want that service pass ---- vdev sleep when idle, and that is actually a service that will register itself, and if it detects by whatever detecting mechanism it has built in, that it just gets called as a service and says, hey, I might just sleep for a little while, or do whatever mechanism you wanted to do to save CPU power. So I see service cores as a library to enable all of these services. And the more there are, the more power service cores library gets, because it means we can do finer granularity scheduling across all the cores. So it is kind of a case of the more we use this, the more everyone else benefits as well.
Okay. And last question is, do you see the POMO drivers implicitly assigning things to service cores, or will the users of DPDK actually get the option to do that?
Again, a service only registers itself. It's not aware of which L core is going to call it. It's not aware of anything. The only thing that the service itself is aware of is the fact that it needs to be called, and hence it registers itself as a service. All orchestration and control kind of plane things should be done at that level. So control plane not part of the service core's library infrastructure itself. Keeping in mind, service cores is actually implemented inside Linux app /EAL, or a common, depending on exact semantics. But I hope that answers your question. Otherwise, please do follow up with me later on. I'd be happy to talk. Stephen.
Well, I'm glad to see this. It seems like another reinvention of the performance lightweight threads that was before proposed several years ago and never went very far.
I'm glad to hear the question. So when we were doing this service cores library, we were looking at it first from a single core doing event dev software, Pulmo driver. So we were looking at it from a very abstract and L core perspective. If we look at it now, and this has come back to me a few times, so it's a very good one to bring up here, and I'm glad it's being communicated to everyone. If you look at it now, it looks much more like a scheduler of tasks than it did initially. So you could say, yes, that there's various options we could look at with doing either kind of a pthreads backend, which was suggested by one of the guys on the DPDK team, like, look, could we not use the existing OS scheduler and pthreads in order to achieve the same functionality? It's possible to get something quite close, exactly the same, I'm not sure. Is it worth the value? I'm also not sure. I haven't done the work. So
the value is if you haven't really defined the model of what those work elements are, like about how long they're allowed to take. Are they allowed to do a syscall to go read something because that was something you wanted them to do? But if you did and you're cooperating, then you just killed the other service, and especially if this scales up to large amount of usage. So at some point you start to say it becomes general purpose. I reinvented pthreads. I want the OS scheduler to be involved because I want to overbook. And so
very good concerns. Absolutely. Please chime in on the mailing list with these type of comments.
Well,
It'd be great to get more of this feedback.
The other thing is if you can just keep the API and worry about what the implementation on the back end is, can change as the usage model gets bigger.
So it's very abstract at the moment. There's very little implementation details being shared about what is a service core or an implementation. I reworked the API a few iterations to try and hide everything. So everything's just integer and some particular
And then
parameter.
there's the issue of how much cross-dependencies, like can you let a Pulmo driver that isn't the softnik go start demanding this, or others not, or maybe you do want it to, you know.
I'm not following your question.
I mean, I could think of cases like a Pulmo driver that has a shared resource that needs to be pulled across multiple threads that wants to have one polar rather than having a spin lock or something else.
Sure.
But then if you start doing that, you push into, oh, the application better have set up a service core, otherwise they're not going to get anywhere.
Right, so I think there's two things there. One is, I'm getting the time up symbol over here. I'll answer that offline if that's okay, Stephen. I'd be happy to discuss it.
Just one question, Harry. So is there a way for the application to know whether it needs to use that service core or not? So can it probe and say, okay, this is going to be software backed. I know that core is going to be used for services. I can't use it for the rest of my application.
So the core is taken from the application core mask anyway. If you do an L core for each launch, it's not going to launch on the service core, so it's hidden away. In order to find out, does the application actually need to manually specify your service core stuff? No, DPDK will, like EAL, will provide a default mapping for everything, so it will just work. In order to get an ideal configuration, the application might have to intervene with use case specific knowledge. Yes, there's an RT service count. So if there is a service, if count is greater than 0, you know that there's something to be done. That something registered a service in order, basically the application switches its logic on that. Do I need to do stuff with service cores, or am I totally service free?
Okay, great, thanks.
Thanks very much, guys.
Okay, thank you very much, Harry.